tutorial starts with a song, but it's only a few seconds long.
Computer animation. Computer animation. Computer animation.
Let's get started with animation.
Hi friends, it's in the middle of the night, everybody's asleep in the house, and my voice is very quiet sort of, and I hope you understand me all right. This is Wolfram Alpha. It's one of my favorite apps on my mobile device, and it used to be one of my favorite web pages in the past. You can type in anything basically, and Wolfram Alpha tries to explain what it is. For example, define triangulate, and then you get a definition of the triangulation, which is a mathematical term. We'll go back to mathematics soon, but let's try something totally different. The ethnic distribution in India, for example. And then it takes a few seconds until everything is being computed, and then you find all the languages present in India, etc. Hello all Indian watchers of my videos, you're very welcome, like everybody else, of course. Let's go to mathematics. X plus, well, 55, for example. That is an equation which is interpreted as y equals x plus 55, and you get a straight line like this. Now let's go a little bit deeper into mathematics. Sine of x times tangent of z. What does that produce? Needs to think a little bit. We have equations and 2D visualizations, and we have this very, very cool 3D visualization. And how do we reproduce this in Maya? Well, let me first create something very simple. Under the Create menu here, you find the locator. It is not going to be rendered, it's just sitting there, and it has dimensions and translation, rotation, scale. Scale doesn't matter here, but it's sitting in the center of the scene. And I want this locator to control the height of a sphere. That's why I create a sphere now. For example, this one. I move it a little bit up so it's separated from the locator here. And I want the locator to, when I move the locator to the right, I want the sphere to move to the right as well. And the same in the other axis, X and Z, that is. It's not in Y. I don't care about Y for now. So how do I make this dependency? Well, the dependent thing is the sphere. So I work with a sphere. And here in the outliner, we have the names of the two objects. One is the locator and one is the NURBS sphere. In order to make typing of a mathematical equation simpler, I just shorten this term here. I call it loc. And I call the sphere SPH. So loc and SPH are my two objects now. Well, I want the sphere to be following the locator in X and Z. So here is with the sphere selected, here is X and here is Z. Now I could type directly into this field, and I did this many times in several tutorials, but to have a little bit more overview, I right mouse click here and I create a new expression. It does basically the same thing. Now I select this. It means the sphere translate X parameter, and I middle mouse drag it down here because this is the expression I'm going to write. So the sphere's translation in X should be, and that means equal. I middle mouse drag this down here, but now it's the locator, LOC. So the sphere's translation in X should equal the locator's translation in X. And I create the expression. When I close this window now, I have a well, velvet look here. And when I play the animation, it does nothing, but when I move the locator in this direction, the sphere follows. When I move the locator in this direction, nothing happens, and that's what I'm going to do now. That means picking the sphere again, right mouse click, create a new expression, and now it's about the sphere's translation in X. Middle mouse, drag it down here, equals, and a middle mouse, drag it down here, and now I need to exchange this by the locator because the sphere should follow the locator in the Z direction. Close this, and now I select the locator. I can select it here in the outliner anywhere, and now it does this. Now when I animate the locator, I animate the sphere. It's basically doing the same thing, and when I move the sphere further up or over there, I cannot move it over there because the X and Z are dependent, but the up axis is still free, so it sits there and moves along in the X and Z direction. But now comes the really fancy part, and that has to do with our equation, the sine and tangent equation. Why sine and tangent? Well, it's funky. Right mouse click, create a new expression, because now we're dealing with the Y situation. Middle mouse, drag it down here. So the sphere's translation in Y should be equal to, and now I move this down and I move this down again. And now change a few things. The translate in Y does not equal the sphere's translation, the locator's translation in Y. Sine, we can type in X here, and times locator again. And now we have the tangent. And not Y, but Z. And we create this equation. When we close it and move the locator, we get this motion here, which is the tangent's motion. It shoots up and down like this into the infinite space, basically. When we move it this way, it follows a sine curve, up and down and up and down. And when we move it crosswise, we have a mixture of these two. Now we want to create a surface from that motion. And in order to do this, I found this quite handy. I create several curves. And I go to the top window for this purpose, and I double click this icon here because I want it to be of degree 1, which means linear. The default reset the settings is 3. That's the NURBS curve, but this is a linear curve, which is basically a straight line. So now I press and hold the key X in order to snap it somewhere to the grid, right here, and the same here. And I press enter and I have the first curve. Now I duplicate it, Control D, and I move it. Actually, I want to modify and reset, center the pivot. That means this locator moves back to the curve rather than sitting in the center of the scene. So I duplicated it, it's the second one, and I snap it to the grid here. And I Shift D, duplicate it again, so I have 4 duplicates now. And I think I make them a little bit longer altogether, like this. And that's my preparation for the next step, because I want the locator to follow these lines. And I created 5 of them rather than one which goes like in an S shape, because you will see in a while that I'm going to create a loft, and for the loft I need several curves and not just a single curve. I could use a single curve, but then I would have to cut it into pieces, but this is a clean approach. So what I'll do now is I want to select this curve here and make the locator follow that. And I need to go to animation here. And here I have constrain. And I constrain this by attaching it to a motion path. So the curve is a motion path and the locator follows that motion path. So when I run the simulation now, or animation now, I get this motion. And now comes the trick. And I want to create a new curve from just the motion of the sphere now. And there is no way in Maya to actually do this. But there is a way how to achieve it with some help from outside. And you find the description in the link below. We'll have to search for a script which does create a curve from that motion. And the script, there are several scripts indeed, but this one works just perfectly, and it's very well documented if you want to go get a taste of Python programming. To forget about Python now, because we don't need it for this tutorial. And it was created by Delano Athias, animator, delanimation.com. And here he explains how to convert motion trails to curves in Maya. But what we can easily do now is this. We select his code. And it needs to begin with import Maya commands as MC. I did a tutorial about Python programming for beginners in the past, and here we started with the same line. And now he starts motion trail to curve, instructions, select the animated objects and run that script. That's all we need to do. Lots of comments on his code, and we just select the whole bunch of things until this d equals 3 with the brackets closed, and we copy it. We copy that script. Now we go back to Maya, and in Maya we click down here on the very right bottom, and this opens the script editor. It's basically the things we did. We created a motion path, etc. It's like the protocol. Here is the MEL scripting, and here's the Python scripting, and the script we just copied is a Python script. That's why we just pasted in here. This is the script. It looks more colorful because Maya interprets the lines differently. The comments, for example, are in red, I guess. And now we need to select the curve, the sphere, not the locator, because we want to create a curve from that sphere. And we click here. That runs our Python script. So with the sphere selected, pressing this icon here, we run that script. The mathematics of this script will be performed on the sphere. And it takes a second or two, and then we have a curve. Now we want to do the same thing here. Later we'll create a surface from these new curves. Now we cannot make the sphere follow this curve as a motion path because it's constrained by this motion path already. That's why we go to the curve number 1, and here we have the motion path number 1. We select it and we delete it by just pressing delete. It gives us an error message and we don't care about it, but now that sphere is free again. So we select the second curve and the sphere, and that's a typical thing you can do wrong, and I always get confused as well. We are not constraining the sphere to the curve. We're constraining the locator to the curve. So let's do it again. Curve and locator, and constrain, attach to the motion path. So the second animation looks like this. It looks pretty much the same, but it is not the same, as we'll see when we execute the script. So we select the sphere now, and we reopen our Python script editor, and we still have it in memory, so we paste the same script here, and with the sphere selected we execute it again. This is our second curve, which is quite interesting. Again, we need to select the curve and the motion path, select the motion path and press delete. So we free the locator from that motion path. Now we select the curve number 3, and with the control key the locator, and we constrain the two of them. We select the sphere now, and from that sphere we want to create a curve. We execute the script, and the new curve is pretty flat here. Now we select curve number 3 again, select the motion path, press delete. Now we go on to curve 4 and the locator, and we constrain it. Animation looks like this. And now we select the sphere, reopen the script editor, paste our script, execute the script, and finally curve number 5, but not yet. We need to free the sphere from the motion path here, so we select it and delete it. And now we select the 5th and the locator, not the sphere. We want to attach the motion of the locator to that curve. Motion path right here. So that's the motion we have now. Now we select the sphere again, open the script editor, paste the Python script, which is a really excellent script because it never produces any faults. If you have a very long animation, it is robust enough to execute it all right, and you see it's doing fine. Now we have interesting new curves, so we can hide these, and we select these, and we create a loft. And we can reverse the surface, so we go to modeling and surfaces and reverse the direction. When you create a loft, select it, and here you see the loft. You have the choice to create more section spans. The default is 1. And I think we can use many more here in order to get a more interesting resolution. And from there you can go on anywhere. Try other functions, for example sine x and cosine z. Interesting. And with this I'll leave you for now, show you a few examples, and have a nice day. Bye.